We are back for the attack, and today we're going to take a look at AC analysis with differential equations, and then we're actually going to correlate it to what we've been working with in what we will be working with in Chapter 9 as well as Chapter 10 with basically phasor analysis, sinusoidal steady state analysis. But I want to kind of show you guys like how to do AC analysis when we introduce essentially alternating current into parallel platform here. And then from there, we're actually going to see why at some point we may not actually really care about the transient phase. We may actually only care about how the system operates in steady state. And I want to show you guys that the result that we get from doing basically AC analysis with differential equations, derived directly from KCL, is actually going to produce the same steady state solution that we would actually get with phasor arithmetic. But with phasor analysis and impedances, we are going to essentially take what we're going to see is 2 whiteboards worth of calculations in linear algebra, and then we're going to calculate that steady state within 3 lines. It's really, really simplistic. So for this problem, I actually just went ahead and just said that the initial conditions were just 0. The capacitor voltage would be 0. The inductor current would actually be 0 as well. And here we're going to find VC of t. It's the easiest way to make a correlation for between AC analysis with differential equations and then with phasor arithmetic. So here I went ahead and just said we had essentially a current source of 40 cosine of 377t. You know what that means, 377t, or the angular frequency of 377 radians per second. That's actually 60 hertz. So I said, but with u of t. So essentially, as we see right here, circuit's not doing anything, but at t equals 0, we're going to turn on this current source, and we're going to allow for a transient phase to happen, in which we will eventually gain that steady state that we're really going to be concerned with. And what we're going to see is that this is actually going to work like a critically damped system. So here we got 25 ohms, 25 henries, and then 10 millifarads. We're going to be looking for VC of t, but by KCL, we know that all these elements here, they're in parallel. And so we know that all the currents are going to be different. So IR of t is going to be different from IL of t, and also different from IC of t. So simply by KCL, IC of t plus IR of t plus IL of t is equal to 40 cosine 377t amps. Go ahead and expand that out by their current voltage characteristics, and we get C dVCT dt plus VR of t divided by R plus 1 over L times the integral of 0 to t of VL tau d tau plus IL of 0 plus, which is equal to 40 cosine of 377t. So for this one, I'm just going to solve it with it being in the integral form. So I'm going to go ahead and isolate the highest order derivative. And I'm just, because we know that parallel elements all have the same voltage, I'm just going to say that V of t is just going to be the same variable here. So dVt dt plus 1 over RC, V of t plus 1 over LC, the integral from 0 to t of V tau d tau plus IL of 0 plus, now divided by C, and also 40 cosine 377t divided by C as well. And so the final equation that we get, IL of 0 plus is actually 0, so it doesn't really matter. But we can quickly see right here with dVt dt plus 4vt plus 4 times the integral of V tau d tau that we got a critically damped system. We're going to have repeated roots here. And then on the right side, we get 4,000 cosine of 377t. So if we take the Laplace transform, we get S as V of S minus V of 0 plus, remember that's 0 volts, doesn't matter for us, plus 4 V of S plus 4 V of S divided by S, remember that. Also remember that if we did have that initial condition in there, it would have to be divided by S too. And that's equal now to 4,000 S over S squared plus the angular frequency squared. So that's the form of the Laplace transformation of our cosine right there. Now we've seen with the underdamped cases, the Laplace transform for an exponential multiplied by the cosine. We saw that, remember that's usually what we see for those underdamped cases when we get oscillation within the transient period. So here, we want to get rid of that s on the bottom in the denominator. So we go ahead and multiply both sides by s, rearrange the equation in which we factor out V of s, that's our common variable that we're looking for, voltage across the capacitor and frequency domain. So we get s squared plus 4s plus 4 times V of s, and that's going to be equal now to 4,000 s squared over s squared plus 377 squared. So note here, I'm leaving this in terms of 377 squared, and I'm doing that on purpose because we're going to see later. It's just going to help us later when we take the inverse Laplace transform, and it doesn't really do much for us until we're developing our matrices. So I just leave it in that form just to keep things cool. So what we're going to start seeing now is probably going, actually may not give you guys a headache at all. Gave me a little bit of a headache when I was writing out all the calculations, but it's really not that bad. However, especially for this problem, because we didn't have any initial conditions. You'll see in the second example that I do where an underdamped case exists, we actually have the initial conditions in the circuit, and it makes developing our matrices and also with the partial fraction expansion a little bit more complex. But how do we actually do the partial fraction expansion when we actually have the Laplace transformation of a cosine in there? Well, we're going to see that. Actually, I had to dig for that a little bit. So let's take a look. I'll move down the camera. I'm actually doing this in a different room tonight, just for posterity's sake. It's going to be interesting when I upload this if I hear this echo, all the way through on the YouTube video. So here, for the partial fraction expansion, here we've got 4,000 V of s. Once we've gone ahead and isolated, we divide through and solve for V of s, then we get s squared plus 377 squared plus s plus 2 squared. So when we actually do the partial fraction expansion for basically s squared plus 377 squared, we actually get as plus b in the numerator over s squared plus 377 squared. Okay, so that's a little bit different right there. We get as plus b over s squared plus 377 squared. And then normally, just like we do for the s plus 2 squared, just partial fraction expansion, just for that, we get c over s plus 2 plus d over s plus 2 squared. So what we want to do now, in order to find a and b, we need to go ahead and just separate those two in the partial fraction expansion just one more time. So we get basically a term of a of s over s squared plus 377 squared plus b over s squared plus 377 squared plus c over s plus 2 plus d over s plus 2 squared. So we go ahead and take the the denominator on the left-hand side, multiply both sides by that, and basically we get our equation that we could go ahead and develop that matrix for. So we get 4,000 squared plus s times s plus 2 squared times a plus s plus 2 squared times b, and then s squared plus 377 squared times s plus 2 times c, and then s squared plus 377 squared, and then that times d. And so now we have an equation that we can go ahead and develop a matrix for. So basically just as we've done throughout this whole class so far, s is equal to 0, s is equal to 1, s is equal to 2, s is equal to 3. And from there we just substitute in just like we normally have done. We have 4 coefficients that we need. We need a, b, c, and d. So we need 4 equations, 4 simultaneous equations. So we go ahead and by substituting s is equal to 0, 1, and 2, and 3, don't care how you guys do it, just as long as it's correct as far as the variables of a, b, and c, and d at the end of your calculations. Here, went ahead and developed these 4 simultaneous equations, put it into my matrix, and then row reduce that sucker. Yeah, we did. And we get a is equal to 0.1. Man, that's really low compared to b, which is equal to 3999.7. C is equal to minus 0.1. D is equal to 0.1. Those numbers look really, really odd. Yeah, they look a little bit odd right there. Let's see if we can make them not look so odd. So if we go ahead and just substitute that back into this equation that we had up here, so we get Vs is equal to 0.1s over s squared plus 377 squared. But note right here, plus 39999.7 over s squared plus 377 squared. How do we take the inverse Laplace transform of that? Let's come back to that in just a sec. Go ahead and put in what we know is negative 0.1 for c over s plus 2. We know what to do with that. And plus 0.1 over s plus 2 squared. We know what to do with that as well. So let's talk about this second portion right here. The Laplace transformation of a sine wave actually has omega, the angular frequency, in basically that numerator. And so if we go ahead and stay consistent, remember this stays consistent right here for the cosine. But for the sine wave, if we go ahead and take out 377, well, we actually get a true coefficient of basically this partial fraction expanded term right here of 10.6 times 377, we just factor that out, over s squared plus 377 squared. And then over here, just as we had before, stays the same, negative 0.1 over s plus 2 plus 0.1 over s plus 2 squared. Now we have something that we can take the inverse Laplace transformation of for all of v of s. You guys are probably scratching your head right now going, God, we got to do AC analysis the whole time with this? Nah, no, we don't. But might as well go that extra step, right? Might as well do the extra step. Helps you in the long run. What doesn't kill you makes you stronger. Your time for revenge is at hand. So we take the inverse Laplace transformation of v of s. And that's equal to v of t, and that's equal to 0.1 cosine 377t. 377 radians per second, right? 10.6 sine of 377t. Let's go ahead and convert that into a cosine. So I'm going to convert that right over. We get 10.6 cosine 377t minus 90 degrees. And then just as we would expect here, we get the exponential portion, minus 0.1 e to the negative 2t plus 0.1 t e to the negative 2t. But let's go ahead and just combine both of these cosines together. And so when we do that, we have to either use an identity or, obviously we have to use a cosine identity to add those two together. I actually just went ahead and utilized Phasor arithmetic just because it was super easy to do. And got 10.6 cosine of 377. Whoopsie. Gotta put that t in there. No, kind of. Well, you can see. 377t minus 89.46 degrees minus 0.1 e to the negative 2t. And then plus 0.1 t e to the negative 2t volts. This is our transient period right here, and this represents really our cosine wave. So, our steady state condition here. So we actually do have a sinusoidal steady state as a result of basically introducing that AC waveform within that circuit and giving this AC form of voltage across that capacitor. So let's go through sinusoidal steady state analysis with phasors, not worry about the transient, and actually go ahead and see if we get the same steady state solution. Well, if we look right here, guys, man, if you look at the book, I plotted this, and you don't really see much of that transient. And so this is a good example of why we may not really care about this. This is so small right here. Very, 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 very small transient period that we actually introduce into the voltage across that capacitor. And so we may actually just only care about that steady state solution. And yeah, this is so almost borderline negligible. Why spend this entire time, other than the fact that it is really cool, to do all this work when we can actually just convert everything over into its impedance equivalence and just solve with phasor arithmetic and be done? Well, let's do it. So keep in mind, 10.6 cosine 377t, what looks like a t, minus 89.46 degrees. It's our steady state solution. Let's see if we get the same thing. Moving the camera over, one more. All right. So the absolute first thing that we have to do with sinusoidal steady state analysis is we need to take this entire circuit that we had at the very beginning. Remember, we don't care about the transient period. It's done. Don't care about that transient period. We just, it doesn't even exist to us. It's not of concern. So we're going to go ahead. We don't have to worry about initial conditions anymore, any of that stuff. But we want to find the steady state for V of t. So we go ahead and convert the circuit over into its impedance equivalent. Obviously, for cosine of 377t, phase angle is 0. But we conserve omega into z of L and z of c. So z of L is equal to j omega L, which is equal to J377 times 25 henries. That gives us J9435 ohms, right? This is all in ohms now because we're utilizing impedance. ZC is equal to 1 over j omega c, which is equal to minus j over 377 times 10 millifarads, or 10 times 10 to the negative third, which is equal to minus j 0.2653 ohms. Oh, let's write that in there correctly there. There we go. All right, so go ahead and write our values that we got here. 50 J9435, and then minus J 0.2653 ohms. So guys, all we have to do, we have 4 parallel elements. We need to just combine all those together into their equivalent impedance. And then, just like we did with just strict resistive circuits, multiply it by that current source, and we're done. Sure enough, ZQ is equal to 1 over the summation of the reciprocals. Here, 1 over 50 plus 1 over j, 9345 plus 1 over negative j 0.2653. And that comes out to be equal to 0.2653. An angle, whoa, that looks very, very familiar. Negative 89.39 degrees ohms. Go ahead, we multiply that by 40 at an angle of 0 degrees. And sure enough, that current multiplied by that impedance gives us 10.61 at an angle of negative 89.39 degrees. And we know that if we go ahead and convert that into the time domain, back into the time domain, here we get VC of t is equal to 10.61 cosine 377t minus 89.39 degrees volts. Good, it worked. It's close enough. Maybe slightly off, but pretty dang close. So, guys, this is really where we're going with chapter 9 and 10 in terms of phasor arithmetic. It just gives us the ability not to have to worry about the steady state. Therefore, we don't have to worry about the differential equation aspect of that when solving and performing this type of analysis. So it gives us a little bit of a break. Just like we've talked about in class, we basically convert the circuit over into its impedance equivalents and phasor equivalents, and we solve with just resistive techniques. Same principles that we did in circuits 1, we're just using complex numbers now. That's the trade-off. So, see you next time.